I'd like to do a review with you here on how to order rock layers. So this is based on the ICA that you did on Monday. And in case you weren't quite sure how things should have worked out with that or how to reason through this, I just want to talk you through it on this video so that you're prepared for the upcoming quiz and then later for the test. All right, so let's review some of the geologic principles that we talked about in class on Monday. First of all, we talked about superposition. This is the idea that rocks on the bottom are older than rocks on top. So if we start building up rock layers through sedimentation and building them up, and these old rocks form first, and then as more layers are formed, we're going to get younger rocks on top. Okay, so that's a general principle for sedimentary rocks. That also leads us into the second idea of horizontality, that sedimentary rocks form horizontally. Okay, they don't form in a tilted way, they form horizontally. All right, and then we have an unconformity. This is evidence in a break in the record. So there's a break in time, something else happens. So this is often associated with tilting. So if we have our original rock layers and some sort of plate tectonic process causes them to tilt, in this case they tilted sort of in this direction. Now our old rocks are here and our young rocks are here, and we might get some new sedimentation on top. Okay, so do you see how this new sedimentation is at a different angle than the others? And so this is the youngest of all because it happens after our original rocks are tilted. Okay, so this break in here is an unconformity. We also have cross-cutting relationships. This is where you have older rocks cut by younger rocks. So let's say we have this whole rock system here that we built, and this is going to now become our new, well, not new, our old system of rocks, and something new is going to happen to them. We're going to get magma coming up, welling up from underneath, and you might get some kind of a piece like this. Maybe it's infusing in the cracks, a crack that is rising to the surface. And so this magma kind of intrudes upon the rock system. Okay, so if we're trying to determine which is older, the sedimentary rocks or the magma, we're going to say the sedimentary rocks are older and the magma is the youngest of all. Now this can be a little confusing because there is magma here at the lowest level, right? It came up from below, but it is younger, even though it's down there, because it cuts across pre-existing layers. Okay, so anytime you notice a process cutting across layers, it's going to be younger than those layers. So this is an example of igneous rocks. You know, magma coming up, hardening in between those rocks. Other features, like a river, you might get on the surface. A river starts to cut away at the rock layers, cuts through. Okay, again, that's a cross-cutting process, and so the river is younger than those layers. And the last thing to mention here are inclusions. This is where you have older pieces of rock surrounded by younger ones. So let's say you have another one of these magma deposits. So the magma comes up, it gets hardened into rock, and inside it are these big boulders, pieces of either metamorphic rock or sedimentary rock that get sort of included within the magma. The magma then is going to be younger than the rocks that are in it. So those are older because they were pre-existing before the magma came along. Okay, so that's how we're going to work on time relationships for inclusions. So let's look at this example. We have layers A, B, and C. First thing to ask is which layer was deposited first. So here we're looking only at sedimentary rocks, and so we're going to start looking at the bottom and say, well, A is on the bottom, and so A formed first. And we're always going to put the oldest things on the bottom. And B formed on top of A, and then C formed on top of it. But as you know, they couldn't have formed at this tilted angle. They had to form horizontally, so we can sort of go back in time and say, well, originally A was like this, and then B was on top, and then C, and then something happened to tilt the whole thing over. And so that's how we got this process. So the tilting happened after C was deposited. Okay, and along with tilting, we also had erosion to give us this smooth horizontal surface on top. Well, later we can have additional sediment accumulating. Okay, so our level D happened much later than A, B, and C because it cuts across. Okay, so back to our time scale here, we have A being the oldest, then we had B, we had C, we had this tilting and erosion, and then last of all, we have D. Okay, do you see that process there? How that unconformity surface tells us what happened in between C and D. All right, so here is the diagram that you worked on for your ICA, and we want to try to determine what order these processes happened in. Okay, so I always think it's easiest to think about the two extremes, which is the very oldest, which is the very youngest, and then we can sort of arrange everything else in between that. So when I start thinking about oldest, I'm going to look on the bottom. Okay, so our bottom choices are either E or G, right? Well, which one is going to be older? When I look at G, I notice it is cross-cutting. Okay, what do we know about cross-cutting relationships? The rock that is cutting across is always younger than the rocks it's cutting across. So we know G has to be younger than E and D and F and C. Okay, so G is definitely not the oldest, even though it's on the bottom. Okay, so I'm going to look toward E as my oldest rock, because it's on the bottom and it's not cross-cutting anything. All right, so I have to kind of reorient myself because E had to be horizontal when it was formed, and now it's not. So originally we would have had E down here, and then D comes on top of it, and then next comes F, right? We have E, we have D, we have F, all being formed at the same angle. So we know that they all had to tilt together. Okay, so E, and then we have D, then we have F, and then we have the whole thing tilting to the side. So I'll just put in here in parentheses. After E, or sorry, this should not be F, or E, this should be F. Okay, so after F formed, then the whole system tilted to the side. Went this direction. Okay? Well, what came, maybe I'll stop down there. Let's go to the top. So we have our bottom started. Top, well, that's pretty easy. What's the very top layer? It's A. Nothing got deposited on top of A. And you can also tell that B is going to be right under it. B had to come right before A. And C had to come before B, so we know that C is in here. So we've got everything lined up except for this G. What are we going to do with G? Well, I mentioned that G has to be younger than everything that it cross-cuts. Okay, so it has to be younger than E, younger than D, younger than F, younger than C, right? Because it's cutting across C, but B is on top of it. Okay, so G has to be between B and C. All right. Another thing to ask about this is we have this fault line here, this red line. The question is, when did that fault occur? Well, we'll start at the bottom again. We know that it had to occur after E was formed because E was affected by it, right? E got offset by the movement on the fault. We know it had to be after D because D got offset. We know it had to be after C because C was affected by it. But what about B? The fault line ends at the top of B, but it does not enter into A. Okay, so we know that B had to be present when the fault moved, but A was not. And so our fault happened in between B and A. All right, next question. We have a feature on top of the land up here that is cutting through the rock. What kind of feature acts like that? Okay, a number of people said an earthquake. The reason I'm thinking it's not an earthquake is because an earthquake would show a fault into the rock somewhere. This one does not show any fault lines. All we see is this sort of gouging out, this cross-cutting. And so this is due to a river. Maybe it's the beginning of a Grand Canyon. You know, you could imagine that over time, this will continue to dig down. You know, maybe it'll reach into some of these other layers, and you could get a canyon forming. What type of rock is E most likely to be? I gave you 4 choices: marble, quartz, granite, and shale. And in this case, we're looking for a sedimentary rock. And so from those choices, shale is your best choice. What kind of rock is G? And I mentioned that G sort of intruded upon everything with this cross-cutting relationship. It's not a sedimentary rock. It did not form horizontally. G is igneous. So this is magma that pushed up through the layers. So is that most likely to be marble, quartz, granite, or shale? Well, obviously not shale because we already used that and that's sedimentary. This is most likely granite. Okay, an igneous rock that hardens underground is often granite. Let's see. Identify a place on the diagram and mark it with an X where contact metamorphism might have occurred. We'll get a different color here. Maybe we'll do green. Oh, we'll do light blue. Okay, contact metamorphism. Remember, this is rock that has been changed due to contact with something hot. Where did we have something hot? Right here. Okay, so this is igneous rock, but where the igneous rock came into contact with other kinds of rock, you can get metamorphism. Okay, so the heat surrounding this sedimentary rock right here would potentially, cook it, turn it into something else. And so that could be a place of metamorphism. Any of these inclusions is a really good candidate for metamorphism to happen. Also along the edges. So here where you have a sedimentary rock that comes up against a piece of granite that hardened, you can get this contact metamorphism. And so if this layer here, the C layer, happened to be limestone, then right where that came into contact with the granite, you might get marble, right? Because limestone turns into marble when it gets heated. So those are sort of the main features going on here.